Thank you so much, Georgios. I'm perfectly okay if you want to stop me and ask me questions from time to time. I will also stop to ask you whether everything is clear. Thank you so much for a great introduction, for pronouncing my name pretty good, actually, surprisingly. And thank you so much for welcoming me here. So yeah, today I'm going to talk about how we can incorporate the cooperation in the main field game setting. The first part of the talk is going to be a little bit more theoretical, where we are going to look at the models from a general mathematical form. Then later on, I'm going to look at a motivating example where we model the fishermen groups with interacting with the fish stock. So that part will be a little bit more applied with numerical results too. So again, if you have any questions, feel free to ask me in the meantime. This is a joint work with Mathieu Lauriere, who is in NYU Shanghai. So what was the motivation for this problem? By the way, I presented it to some of you before, so it's going to be a little bit extended and slower version of it. So if there was something not clear to you in my previous presentation, hopefully this time it will be a little bit in more detail. So the reason I started this thing is actually coming from my undergraduate years. Like when I was in undergraduate years, I got a course on agent-based simulation, and my term project was modeling the tragedy of the commons. And my minor was in economics, so I was very interested in this type of phenomenon, such as the tragedy of the commons, to understand how the individual's behavior affect the long-term outcomes. So with this interest, I started doing some research on mean field game, and I realized actually sometimes it is hard to model this type of problems in this mathematical formulation of mean field games. And with this motivation, we started doing this. So tragedy of the commons, for the people who may not be familiar with it, is that it's the short-sighted overconsumption of the common pool resources. This can be, for example, the fish stock, the coffee, or public parks, or underground water, that may lead to long-term detrimental results. The idea is that every individual is basically trying to maximize their own objective, and at the end they are over-consuming, and the stock is being depleted, and in the long term, actually, they don't have anything to consume. So in real life, what happens is that actually this phenomenon is not observed commonly. Some of the researchers are saying that this might be because of the governing laws. It can be like some incentives on taxations, or it can be due to individualistic efforts, such as people individually thinking that they shouldn't overconsume. So Elinor Ostrom actually is one of the main researchers who worked on the latter, and she actually got a Nobel Prize in 2009 in economics related to her work on this topic. So what we want to do is that basically we want to model the possible altruism and the individualistic efforts of the individuals in the large populations to prevent the tragedy of the commons to happen. So before going into the detail, I'm going to be talking about mathematical frameworks such as the mean field games and mean field control and the combination of them. So before going into detail, maybe we can talk a little bit about these two problems. So what happens in that? In the large population games, due to increasing number of interactions, it is pretty challenging to find the solutions. So here I put solutions because, for example, if we are looking at the mean field games, we are looking at a fully competitive setting or fully non-cooperative setting. And in this setting, we generally look for the Nash equilibrium. But if you're looking at the mean field control setting, this is going to be the case where we are going to assume that all the individuals are cooperating with each other and they are trying to minimize their aggregate or average outcome. So in this case, we would look for social optimum. So depending on what type of setting we look at, the solutions in these problems will be changing. So, but in both of these cases, since we have exponentially increasing number of interactions among the agents, and since we need to account for these interactions, it is going to be pretty challenging to find this. So what we do is that generally we use mean field approximations. As I said, for the cooperative setting, this would be mean field control, or sometimes it is called control of Mackin-Vlasov dynamics. If you are looking for the competitive setup, this would be mean field game setting, where you look for mean field Nash equilibria that is going to approximate the Nash equilibrium in the large population games. So both of these models have similarities. In both of the cases, from the name, you may understand that we are looking at a limit, mean field limit. So we assume the number of players goes to infinity, and we assume that agents are identical and infinitesimal, and agents interact symmetrically through their mean field interactions. So this means that, for example, they are not going to account for each other's interactions directly. Instead, they are going to be interacting through the population distribution of, for example, states, controls, or in general distribution. So in this setting, since we assume that everyone is identical and they interact symmetrically, we can focus on a representative agent and this representative agent's interactions with the distribution. So what is the difference? In the mean field game, as I said, we are going to look at the non-cooperative or competitive agents. In the mean field control, we are going to look at the cooperative agents. And I'm going to discuss a little bit the differences in the definition of these solutions later on. But I want to comment here one thing, like even if we have a very restrictive looking problem, these settings are extended to the cases to include heterogeneities. For example, you can look at multi-population mean field models, you can look at major minor mean field models, or you can look at like Steckelberg mean field models. So this type of basic assumptions can be relaxed. Okay, so here I'm going to start a little bit math. So like from time to time, I will get involved with a little bit mathematical things, but most of the time I am just going to specify where are the important things you need to be careful at. So here I'm going to assume that the models I'm going to look at first, they are dynamic, they are continuous time, and they are stochastic. So I'm going to assume that the representative agent state process is going to have this like a pretty general dynamics where xt is the state of the agent, alpha is the control of the agent, mu t is the distribution in the population. Again, this can be like the distribution of the states, distribution of the controls. It can be population statistics too. It can be, for example, in the LQ games, we generally take this as the average of the states, expected state. And we have some randomness that comes from the Brownian motion. Oops, sorry. So the difference between mean field game and mean field control, I wanted to put this slide because I think it shows the solution, like a solution from the mathematical point of view pretty clearly. So for the mean field game, what we do is that since everyone is individual, we are going to focus on the best response of the agent by basically taking the population distribution as constant. And we are going to find the best response of the one individual. Then, since everyone is identical, we are going to assume that everyone should behave similarly. So we are going to say that the population distribution that we fixed at the beginning should be actually the distribution of the state that is induced by the best response found by the representative agent. So this is going to create a two condition setting for the definition of the mean field game Nash equilibria. First, we need to find the best response. And second, we need to find the fixed point. So one thing here is that if you realize specifically from the mathematical notation point of view, the best response is the one that is going to be minimizing the cost when we fix the population distribution. And then this population distribution is going to be the law of the state, where the state is basically the one controlled by the best response action. On the other hand, when we look at the mean field control, what's going to happen is that here, if you realize for the cost function of the mean field game, I put this mu t because we are going to treat this as exogenous when we are finding the best response. But for the mean field control, we don't have a fixed point part. We just have the optimization. What we do is that we assume that everyone is identical, but everyone is cooperating. So like if one of them does something, the others will do similar things. So this will affect the population distribution instead of like we are assuming the population distribution is given by while changing the representative agent's behavior in the mean field game. So then this distribution, the law of the state, should be getting affected by the control of the agent in the mean field control. So when they are optimizing, they should also take into account their like effect on this distribution. Okay. So later on, for the sake of simplicity in the notation, I'm going to use mu t as the population distribution that the agent will take exogenously, and mu t alpha as something that the agent will control, a distribution that have control over the distribution of their own state. So do you have any questions related to the notation, anything? Because after that, we are going to build on these things. Okay.
Gökçe,
And oh yeah.
I have a probably a stupid question.
Oh, no problem.
When we talk about cooperation in a game, typically you'll have a case where the agents are maximizing or minimizing the sum of their payoffs. How this is translated in this mean field control setup?
Yeah, so we take the number of players to infinity. So looking at sum is not pretty good because it will sum to the infinity. So instead we look at the average. So here, since we assume everyone is identical, this expectation is going to treat it as the average cost, since we are also going to assume that the distribution will be changing with the year behavior.
Okay,
Yeah.
okay. It's clear.
Yeah,
Thank you.
that's a very good question. Thank you so much. Okay. So from the common pool resource modeling point of views, why don't we just use mean field games or mean field control? So if we look at it, mean field game is the case where the agents are insignificant and they do not see their effect on the system at all. So if we use mean field games, they are going to overuse the resources. So in these models, tragedy of the commons will be inevitable. But if you look at the fully mean field control case, what's going to happen is that agents are going to be assumed fully altruistic. And this thing is that not very good representation of the human nature, because as we can all like confess, is that we have some individualistic thoughts in our minds, and we are not always fully altruistic. So what we want to do is that we want to model the mixture of these type of behaviors, either at the individual level, where we assume that individuals are partially like altruistic, or at the population level, where we assume that some people are altruistic, but some people are still in the non-cooperative setting. So I'm going to talk a little bit about a related literature. Surprisingly, there were not too many work on this. Some most related papers to this was like Anguli, Diterek-Fook, and Lauriere. They had something called mean field control games, where actually they have a competition among infinitely many groups of cooperative agents. So this is a little bit related to our mixed individual case. And on the other hand, where Gomez, Duncan, and Tambin, they have something called cooperative linear quadratic mean field games. So what happens in this paper is that they are they are looking at one representative agent, and they have their this representative agent's objective, but they add the other agent's objective with some alpha parameter to the objective of the representative agent. So in this way, the agent also sees other people's objectives. So depending whether this alpha is positive or negative, the agent may be altruistic or even more in the negative perception of others to like maximize others' cost. So our setting is going to be different than this, but like the idea of modeling the altruism, that motivation is similar. Today, I'm going to mostly talk about the paper with the same title, but we did some related work, especially like last year, we presented a work in CDC where we do the LQ version of this without the common pool resources. So if you're interested in the LQ ones without common pool resources, you can check that one. And we also did a little bit the relationship between mean field game and mean field control and how we can move from one of them to the other one, vice versa, in another paper with René Carmona and François Delury and Mathieu again. So I'm going to consider two setups in this talk. The first one is going to be, as I said, mixed individual. This is going to be the one where I'm going to assume that every agent is going to have some altruistic tendencies as well as non-cooperative tendencies. On the mixed population case, we are going to assume that some people are fully altruistic and some people are fully non-cooperative. So this may look like if the proportions are similar, they may result in similar results, but we are going to see actually they are going to end up with different results, even if the altruism levels are the same at the population level. Okay, so in terms of outline, we discussed the motivation and introduction to these models, etc. And we are going to discuss next the mixed individual models in the general form. Later, we are going to look at the mixed population ones. And at the end, as I said, we are going to look at the motivating example of Fisher and the fish stock modeling. And we are going to compare the results of mixed individual and mixed population settings. And we are also going to compare this to the mean field game, of course. So let's start with the mixed individual mean field models. So in this one, I'm assuming that we have a large number of homogeneous agents and they each see their individual effect as well as the population effect. So mathematically, this is going to be kind of a combination of a mean field game and mean field control, where I am going to add the distribution of the agents on state on the cost function and dynamics in a mean field game model. So then the cost of the representative agent who is using a control alpha, given the population distribution mu, this is the one that they feel like they don't have any effects on, is going to be given as this. As I said, alpha is the control, xt is the state, mu t is the population distribution. Since we have infinitely many players, the players are insignificant, so they are seeing this exogenously where they are finding their best response. And they are also getting affected by the distribution of their own individual state. So from the intuition level of, from the intuition point of view, we can think of it as like people are seeing some effect of the population and they don't think that they don't have an effect on it. And they also assume that they have some effect on the system. And this mu t alpha is going to put this effect on the system. So then the representative agent state is going to be affected by a drift that is going to have these two distributions both included. So then we are going to have the definition of the mixed individual mean field Nash equilibrium, a little bit similar to the mean field game, and I'm going to clarify what is the main difference. The best, since it is similar to finding a Nash equilibrium, we need to find the best response. And this best response is going to be found by fixing the population distribution. But at the end, this we need to assume that everyone is behaving similarly because we assume that everyone is identical. So we need to do a fixed point to find the Nash equilibrium. So the distribution that we fixed at the beginning should be the distribution of the state that is induced by this best response. So what is the main difference than mean field game? In a mean field game, when we are finding the best response, actually, when we fix the mu, we just solve a stochastic optimal control problem. However, in this one, we are going to be solving a mean field control problem because even if we fix the mu here, as you see, we have the mu t alpha, so we are adding one layer of complexity. So in order to show some of the theoretical results, here I'm introducing our Hamiltonian as usual as a drift times the adjoint process plus the running cost. And whenever I need to take a derivative with respect to the distribution, it is going to be the derivative on the second distribution because we are taking the population distribution as exogenous, as something that we can't control. And the second one is our individual effect. So then our theorem is basically the characterization of the equilibrium by using some stochastic differential equations. So if you're familiar with the probabilistic approach to mean field game and also mean field control, this is going to look pretty familiar to you. What we are going to have, the adjoint process is going to be basically giving us the derivative of the value function. So here we are going to have a derivative with respect to Hamiltonian, which is similar to the sense of mean field game and mean field control. But we also take the deviations with respect to the second, distribution by adding this second derivative here. This is similar to the sense of mean field control. So in terms of proof idea, as I said, given the population distribution, we realize that actually the problem becomes a mean field control problem. And we basically characterize the solution of this mean field control problem with a forward-backward stochastic differential equation. Then we need to apply this fixed point. And this is done by setting the population distribution equal to the individual state distribution. And at the end, as you realize, these mu's are going to be the same because we assume that people are identical. So in terms of another result, we prove the epsilon Nash equilibrium results for this one, which says that if we solve this problem, we are giving an epsilon approximate Nash equilibrium to the finite player version of the problem. So now let's discuss a little bit how we can introduce the common pool resource modeling to this setting. So we are now going to introduce the state K, which is going to denote the common pool resource stock. And this thing is going to have some replenishment and some decay rate, or you can write a general differential equation for its dynamics. So for the replenishment in the setting, I'm assuming that its replenishment depends on its own stock. So for example, the fish population grows with higher fish population, but it also has some decay. And this decay is going to get affected by the individual's behavior and through also the population of the stock of the common pool resource. So here I'm looking from the lens of the individual and I'm writing this dynamics from their perception, which means that for this decay, they are seeing the population effect, again, exogenously, but they also see their own individual effect. That's why I include both mu-t and mu-t alpha in the decay term. So then with the addition of common pool resources, the whole model is going to become just an extended version of the previous one where we include this new common state, where this one is the individual state, and this common state's dynamics. One thing important here is that we didn't put any noise for the common pool resource because if we put a noise, it should behave as a common noise and it creates many more technicalities and problems for the mean field game in the mean field game type of problems. So for now, for this step, we didn't put common noise. This is possibly our next step for our future work. So our remark, as I said here, if we write this model by extending our state to x check, where it includes the individual state xt and the common pool resource state kt, the same technical analysis we discussed previously will apply. So do you have any questions about it?
Yes.
Yeah.
Yes. Thank you, Gökçe. Very nice talk. I have a conceptual difficulty with the mixed individual, like from a finite game, how will I catch this model?
Yeah, so like there are some different ways, but one way can be, for example, you can think of it as a little bit similar to Anguli et al. Paper, where people are basically, the people are actually cooperative groups, large cooperative groups, and they are deciding in their cooperative groups, then they are competing at the higher level. So it is actually basically in the finite player setting, you can do it like that.
Okay,
So when we
thank
write
you.
a finite player, we generally write it like that. We assume that they have subpopulations. It's like they are like cooperative units. One agent is like a cooperative unit. Does it make
Okay,
sense? Okay.
okay, thank you. I will ask more questions. Thank you.
Okay, perfect. Thank you.
Thank you so much.
Okay, so one spatial, like in the previous one, as you see, I didn't talk about how we combine this individual and the individual and the altruistic parts. But one thing we can do is that we can look at a spatial case, and we will assume that everyone will have the same and constant level of altruism that we denote with 1 minus lambda, and it will be between 0 and 1. So when lambda is equal to 0, the level of altruism is equal to 1. So it is the fully cooperative setting. So it will correspond to mean field control. And when lambda is equal to 1, the altruism level is going to be 0. It is the fully non-cooperative setting, which is going to refer to a mean field game. So then in the modeling, instead of putting this mu t and mu t alpha separately in the general model, you can put the convex combination of them, and they will be basically seeing mu t with alpha weight and their individual effect with 1 minus lambda weight. So after this part, let's discuss a little bit the general formulation of the mixed population mean field models. And after that, we are going to start the motivating example. So in the mixed population case, now we have a large population of fully non-cooperative and cooperative agents in the population mixed together. So we can focus on two representative agents. In this case, because we have one for the non-cooperative and one for the cooperative one. For the non-cooperative one, the problem is going to be a mean field game model given the distribution of the cooperative agents. And for the cooperative one, it is going to be a mean field control model given the distribution of the non-cooperative agents. So then in the formulation, previously in the mixed individual, we had one representative agent, but in this one, we need to have two. And in the formulation of the representative non-cooperative agents, I put here that they see, while they are finding their best response, the distribution of the non-cooperative and cooperative agents exogenously. And for the representative cooperative agents, they are going to see the non-cooperative agents distribution exogenously, but since they are cooperative, we are assuming that they see their own effects. So the mu t that comes from the cooperative part is going to be affected by their own control. So this part is going to behave like a mean field control. So basically, at the end, the best response for the representative non-cooperative agent is going to be found by fixing this. And the optimal control, not best response, for the representative cooperative agent is going to be found by fixing the non-cooperative population distribution. So then here, let's look at the definition of the equilibrium for this one. It is going to actually have three conditions because now we have two representative players. And for the non-cooperative ones, we need to have the best response and the fixed point conditions. And for the cooperative ones, we need to have the optimality condition. So the first thing is that we are going to call a non-cooperative control, a cooperative control, and the non-cooperative population distribution tuple, a mixed population mean field equilibrium, if first the non-cooperative agent gives their best response to basically the population distribution in the non-cooperative part and the population distribution of the cooperative agents. Here, as you realize, I didn't put the population distribution of the like cooperative ones because this is the control setting and it is going to be directly the one that comes from using the cooperative optimal action. The second thing is we need to find a fixed point for the non-cooperative agents because they need to be in the equilibrium. So their distribution is going to be equivalent to the distribution that is induced by their best response. So this part is going to resemble the Minfield game given this extra distribution. And then we have the cooperative optimality, which means that the optimal control for the representative cooperative agent is found by fixing the mean field or the distribution of the non-cooperative agents, so they minimize their cost function by keeping the non-cooperative agents distribution exogenously. So again, we can introduce here the Hamiltonians in a similar manner where we have the drift times the adjoint process plus running cost. Of course, now we have two Hamiltonians because we have two representative agents. So then at the end, we can characterize our equilibrium with some forward-backward stochastic differential equations. We need to have two of these because again, we have two representative agents. For the non-cooperative ones, you are going to have something pretty similar to the Minfield game. And for the cooperative ones, we are going to have something very similar to the Minfield control. Here, the ones that I highlighted are the ones that comes from the Minfield control effect. So the proof idea is pretty straightforward. We write the forward-backward stochastic differential equation that characterizes the Minfield game solution for the non-cooperative agents, while we keep the cooperative agents distribution exogenous. And then we write the forward-backward stochastic differential equation that characterizes the Minfield control solution for the cooperative agents, while we keep the distribution of the non-cooperative agents exogenous. At the end, we need to have the fixed point to set the fact that the non-cooperative agents distribution is the one that comes from their best response. So again, here we show here some approximation results, but this is a little bit non-standard because what happens is that this is, we called it equilibrium, but actually we a little bit struggled naming it because it is an equilibrium and optimality at the same time for the non-cooperative versus cooperative agents respectively. So our approximation result is an approximation for equilibrium for the non-cooperatives, but for the optimality for the cooperative agents. So that's why we needed to have two approximation terms here, epsilon 1 and epsilon 2. Okay, so now the common pool resource part is a little bit interesting. When we first modeled this, we were a little bit puzzled. The difference is that now, different than the previous mixed individual setting, non-cooperative and cooperative agents perceive the world differently, and this also kind of this is also kind of shown in the perception of the dynamics of the common pool resource. So what we are going to do is that this B0K and B1K functions are going to be the same, but what the non-cooperative agents and cooperative agents input in this equations will be slightly different. For the non-cooperative agents, they are going to put this exogenous distributions for the non-cooperative agents and the cooperative agents. But for the cooperative agents, they are going to take the non-cooperative agents' behavior exogenously. But for the cooperative part, since they see their effects, they are going to put this distribution that is affected by their own decision. So they are going to see their own effect on the common pool resource dynamics. The interesting thing is that since at the equilibrium, this thing is going to be equal to each other, what's going to happen is that actually these two dynamics are going to be corresponding to each other. And at the equilibrium, we will have one dynamics for the common pool resource. Again, like if we extend the states to include both individual state and the common pool resource state, the previous technical analysis is going to apply. So here, before going into our motivating example, I want to discuss a little bit another simplification that we called P-mixed Minfield games. So in this one, what's going to happen is that I'm going to assume that there is a fixed proportion P of non-cooperative agents and 1 minus P proportion of the cooperative agents. And then instead of plugging in this distributions separately, as we, for example, do here, we can again input the convex combination of these distributions. So this will be the aggregate distribution in the population that is observed by the non-cooperative agents. And this one where the second distribution shows the direct effect of the cooperative agent is going to be the aggregate distribution that is observed by the cooperative agents. So before going into the motivating example, do you have a question? Okay. You can always stop me, by the way. So in this one, the idea was modeling the Fishers and fish stock. And the fish stock is going to behave as the common pool resources. And of course, Fishers are going to behave as the individual agents. So let's start with the mixed individual Fisher and fish stock model. So we are going to model a large population of fishers with an altruism level of 1 minus lambda. I'm going to look at the spatial case where we use the lambda and later for the mixed population P parameterization. So for the state, we have the fishing effort that is denoted by xt at time t. And the control is the change in the fishing effort alpha t. And the common pool resource is the fish stock level kt. Then we did a little bit research on like what can be tragedy of the commons for a fish stock. So according to World Wildlife Fund, they say that around 25-35% of spawning stock biomass, this is the maximum population the fish can have, is creating a management concern. So in reality, generally, we have around 70% of the spawning stock biomass. And if it is like 50%, etc., that is okay. But if it goes around 25 to 35%, it creates a possible like not replenishment problems, and it creates management concern for this fish population. So that's why we are going to set this level to 30%, so like something between 25 and 35. So after this, let's see how we can model this thing mathematically. By the way, like when we were interested in this thing, we did a little bit literature review and we saw that there is a PhD thesis of McPike, and they are actually interested in modeling fish stock in the Minfield games. So we were very like inspired by their model and kind of like got ideas from them. So here the state dynamics, the individual state is the fishing effort, and this fishing effort is going to be controlled by the change alpha, and we have some noise to reflect maybe like daily effects, some like unexpected problem with the boat, etc. And then we have the common pool resource stock that is shown with KT. Here, this calligraphic K is going to be the spawning stock biomass, and this row, we will set it to 0.7 is the initial fish stock level. And we model here a logistic growth, and we model a decay due to fishing, and the fishing is affected by the fishing effort, average fishing effort in the population. Since we are doing the mixed individual with the altruism level of 1 minus lambda, they are seeing with the 1 minus lambda weight, their effect on this distribution. And with weight lambda, they don't see their effect. This part is taken exogenously. So this is not a LQ model, as you see that we have quadratic dynamics here. So it is going to create some like theoretical difficulties later on when we try to do the existence uniqueness type of proofs, which I will briefly mention later. And for the representative Fisher's cost, we are using the following. They are going to have some costs related to ramping up or down their fishing efforts. For example, like they want to keep it around the same levels, not like they want to fish one day and like not fish like 1 month, etc. and they have high effort cost. Here, this is a little bit more in the quadratic sense, and they have a fishing revenue. This P is the price that comes from the fishing, and this is how much they fished. It is going to depend on their own efforts. It is going to depend how much fish stock was available, and the price is going to be affected by how much fishing was happening in the population. And that's why we have the mean field effects in the pricing function too. So for the pricing function, we chose a linear inverse supply function where this the price is affected by this thing in a negative way. So if there is more fishing, the price is going to be lower. If there is less fishing, the price is going to be higher. So at the end, what we do is that we characterize our mixed individual mean field equilibrium by using the general theorem we introduced previously. We are having some forward dynamics that comes from the individual state, that comes from the common pool resource state, and we have the adjoint processes that are related to each of the states and basically the derivative of the value functions with respect to each of the state. That's why we have two of them. So when we look at this thing, this is actually a little bit more complicated forward-backward equation because this is not an LQ problem. So in order to show the existence uniqueness results, we needed to do a little bit more work. So we showed that under the small time condition, there exists a unique mixed population, mixed individual, sorry, this should be mixed individual mean field equilibrium. So here, how do we do this? First thing that we do is that since I do under small time condition, you may realize that I use Banach-Fix theorem somewhere, but it's not just Banach-Fix theorem, it is two-layer. First, we realize that we can take expectation of these differential equations. And when we take the expectation, we are basically getting rid of the thing is like here, most of the things linear when we take the expectation, so we don't deal with like second moments, etc. The expectation is taken pretty cleanly. Then for this basically for this mean processes, we are applying a Banach-Fix point theorem. So this gives us the under small time condition. So we show that under the small time condition, actually the mean processes exist and unique. So given these existing and unique mean processes, we realize that this differential, this forward-backward stochastic differential equations now become linear because like we are going to treat these things as a like exogenously. So then we can propose a linear ansatz and characterize, we basically reduce the system to a system of ODEs, and then we can show the existence and uniqueness of the ODE system. Like as you may guess, we are going to have some Riccati equation and some linear ODEs, and we use basically results on them to prove the existence and uniqueness of the regular processes, not just the mean processes. So in this way, we are doing a two-level existence and uniqueness proof, where the first two-step brings us the small time condition. Do you have any question? Okay. And then let's look at some numerical results. So here I'm on the left, I have the fish stock level, which is the K, and on the right, it is the average effort. These two are the most important because this is just the effort change. So here, the things that we observe is as follows. As the altruism increases, this means that the lambda is going to decrease. So our color is getting darker and our lines are getting more solid. The fishing stock is going to be lower. This is kind of what we expect, right? When we say that there's some altruism, we would expect the fishing stock to be lower. And then we see that fish stock levels are going to be higher. If you remember, I put a 0.3 as the management concern. And here, only one line, which is this very light blue, very like a sparsely dashed line, is below the management concern, where we can say tragedy of the commons is likely. And this is the case, actually, lambda is equal to 1, and it is corresponding to mean field game. So as you see, mean field game is ending up with an inevitable tragedy of the commons, but when we introduce some part of altruism, we are getting better and better results. Like even if we introduce a little bit, we are able to go above this management concern level. So now we can also discuss the mixed population formulation and give its results, and finally put the comparison of two results. For the mixed population, again, I'm looking at the spatial case where I assume the p proportion of the non-cooperative, we have p proportion of non-cooperative fishers and 1 minus p proportion of the cooperative fishers. So in this case, we are going to focus on two representative players, as I discussed in the general formulation, and we are going to have the representative non-cooperative agents dynamics and the cooperative agents dynamics as follows. So the difference here is, as you can see, for the non-cooperative agent, the non-cooperative average fishing effort and the cooperative average fishing effort are taken exogenously. But for the cooperative agents dynamics, this thing here, the average fishing effort in the cooperative part is taken as something they can observe. They have some control over. So then basically this is going to be their main difference. Even if I introduce the common pool resource dynamics differently due to this different input that is observed by the non-cooperative agents and the cooperative agents, at the equilibrium, actually, they are going to be equivalent to each other, and we are going to have only one common pool resource dynamics. So the cost functions are also similarly to the mixed individual, where we, for the representative agents, have the non-cooperative and cooperative average fishing efforts exogenously. But for the cooperative setting, the cooperative agent see this average fishing effort of the cooperative population as something they can control. Okay. So at the end, we are going to end up with a much more complicated forward-backward stochastic differential equation system. And this is because we have now like two representative agents. Here, I know it looks complicated, like I'm not going to go into too much details of it. The most important thing I want to show is that, as you see, for the common pool resource, I'm going to have only one dynamics. They are going to be equivalent to each other due to the fixed point conditions at the equilibrium. So this common pool resource dynamics is going to be common for both of the agents, which should be because it is the common pool resource. But on the other hand, we have the individual state dynamics separately, and we have the adjoint processes with respect to the individual states and common pool resource separately. So here, again, for the theoretical results, we again show this under small time condition. There exists a unique mixed population mean field equilibrium. The thing is, the proof idea is exactly the same. It's just like you need to be a little bit more careful because the equations are a little bit more complicated, and since now we have higher dimensional things, you need to deal with more like vector notations, etc. But the idea is the same with the previous one, where we take the expectations of the differential equations, show the existence and uniqueness of the mean processes, then plug in this existing and unique mean processes in the FBSD, and realizing now that we have a linear forward-backward stochastic differential equation system, and then basically giving a linear ansatz and showing the existence and uniqueness in the reduced ODE system. So if we look at the results here, basically on the left, I have the fish stock, and on the right, I have the average efforts that we separated for the cooperative and non-cooperative agents. And here, P, as you realize, is the level of the cooperative agent, non-cooperative agents. So what we observe in these things is that when we have the more solid line, it is going to be P equals to 0, which means that everyone is cooperative. When we have the light blue, very sparsely dashed lines, it is going to be P equals to 1, which is the mean field game setting. So this can be like everyone is cooperative. This is everyone is competitive. So what we observe in these plots is that we see that cooperative agents are going to fish less to protect the fish stock levels. So here we look at the cooperative ones, and they are the light blue ones, and the non-cooperative ones are the light green ones, and the non-cooperative ones are the dark green ones. And we can see that at each level of P, the non-cooperative ones are basically fishing more than the cooperative ones. And this shows that the non-cooperative agents are enjoying free riding. So they are basically taking advantage of the efforts of the cooperative agents. The other thing we observe is that as the proportion of the cooperative agents increases, so this is when the P decreases, the fish stock levels are higher. This is something that we already expect. So the most interesting thing comes from the comparison of these two settings, because when we first modeled, we felt like actually for the special cases where the lambda and P is equivalent to each other, at the aggregate level, it corresponds to the same level of altruism. But the thing is we expected in this case actually for them to behave at the population level similarly, but we observed that actually this is not the case. So here I have the comparison of the fish stock with the solid lines. I saw the mixed individual case, and with the dashed lines I show the mixed population case. Again, when the lambda is equal to 1 or P equals to 1, what we have is that everyone is competitive. So as you see that the fish stock is getting lower, and this actually corresponds to the mean field game setting. And when we have a smaller lambda or P, we have more altruism levels, so we have higher levels. So when we look at this thing, what we observe is that for, what we observe is that at the same level of lambda and P, fish stock level is lower and fishing efforts are higher in the mixed population case. So this means that actually when we have totally separated cooperative and competitive agents, there is the free riding effect, right, from the non-cooperative ones, and they are taking advantage of the cooperative agents, and this is reducing the aggregate level efforts. So then we can, for example, say that it is better to have everyone with some altruistic tendencies instead of having a mixture of fully cooperative and fully non-cooperative agents. So, for example, this insight may help actually like giving some kind of idea for the policymakers to increase the efficiency for the common pool resource stocks. So this will, I think, the most interesting thing to me, because, for example, if you look at here, in the management concern, we see that if the population is in the mixed individual setting, we see that only in the case where lambda is equal to 1, it is below the management concern. But if we are in the mixed population setting, we see that for P equals to 1, P equals to 0.7, or P equals to 0.5, we are still below this management concern level. So it is not the same to have 50% of agents totally cooperative and 50% totally non-cooperative, instead of like everyone being 50% altruistic. So I think this was an interesting observation that we had. So here, basically, I'm just going to conclude a little bit with a small summary, and if you have some last questions, I can take them. What we did is that we introduced this like combination of mean field game and mean field control models, where we call mixed individual and mixed population models, and we introduced the modeling of common pool resources in these models. And we discuss equilibrium definitions, characterizations, and spatial cases, and we introduced our motivating example, analyzed it theoretically, and solved it numerically, and discussed some numerical insights. So thank you so much for listening. And if you have any questions, please let me know.